Hi, welcome. In this video, we'll show that if f and g are two quasi-concave functions defined on S, which is a convex subset of Rn, then the function h from S to R, defined as min of fxgx, is also quasi-concave. So let's begin. So in order to show this, we'll show that the upper level set of H is a convex set. Okay, so consider an arbitrary A. Consider an arbitrary A in real line. And if we consider the upper level set PA, it is defined as X in S such that the value of Hx is greater than or equal to A. So I want to show that this is a convex set. Okay. Now notice that Hx is min fxgx, so I can replace Hx by min fxgx, and I'll get that it's a set of all x where smaller of the two is greater than or equal to A. So when I say smaller of the two, fx or gx is greater than or equal to A, that is equivalent to saying that both fx and gx are greater than or equal to A, because if smaller of the two is greater than or equal to A, the other one will also be greater than or equal to A. So an equivalent way of writing this is that x in S such that fx is greater than or equal to A and gx is greater than or equal to A. Now this is something that I can also write it like this, that it's the intersection of these two sets. X such that fx is greater than or equal to A and x such that gx is greater than or equal to A. Now since f is a quasi-concave function, so this set is a convex set, and since g is a quasi-concave function, so this set is a convex set. So it's the intersection of two convex sets, which we already know is a convex set. So because any intersection of any two convex sets is convex. Therefore we have shown that PA is a convex set, and since PA is a convex set and this was an arbitrary A, that means H is a quasi-concave function. Now this is a very interesting result. We can actually think of some examples now, which we can just where we can just apply this definition, where we can just apply this result and say that the function is quasi-concave. For example, if f is a function from R2 plus to R defined as fxy equals x times y, and g is a function from also R2 plus to R, okay, defined as gxy equals maybe x plus y. Okay, now f is a quasi-concave function and g is a quasi-concave function. So if you look at this particular function, which is hxy equals min of xy comma x plus y, this is also quasi-concave. So So that's just a result of this particular theorem. We can just apply this particular theorem and comment on the quasi-concavity of a function like this. So this is just one example, and there are of course several such examples where we can apply this and quickly infer whether the function is quasi-concave or not, just by looking at the function. Okay. Thank you.